Yes, welcome to Easy Gates Electrical Gate 22 paper solutions. Problem number 11. Another interesting problem based on systems, especially the frequency domain. So given a transfer function of a real system h of s that is equal to as plus b divided by a square plus cs plus d. Okay, where a, b, c and d are positive constants. Okay, greater than 0, you can say. This system cannot operate as. So probably you need to pursue the problem in such a way that A is tunable, B is tunable, C is tunable, D is also tunable. Okay, these are the tunable parameters, but they take a value greater than 0, remember. Okay, so then I can write h of s as h of s is equal to as divided by a square plus cs plus d. And this is b divided by a square plus cs plus d. That means, hope you remember the standard models. The standard second order, it is k into, okay, this is looking like k into omega n square by a square plus 2 zeta omega ns plus omega n square. If you make it filter, then you can replace 2 zeta by 1 by q, because q is equal to 1 by 2 zeta, where q is the frequency selectiveness of the filter. So you can either represent the system in terms of damping usually for time domain response, q usually for the frequency domain. So this is how, but anyway, since you are familiar with the damping based second order, but still, okay, that is a function known as a low pass, second order low pass function. So this term is a low pass function. So that's why you're comparing with the standard models. And this one s in the numerator. So constant in the numerator, denominator is second order, and constant in the numerator is a low pass. S in the numerator is a narrow band pass. So this is a narrow band pass function that resembles KPB into the middle term in the numerator, that is 2 zeta omega n into s in the numerator, the whole divided by the standard denominator s square plus 2 zeta omega ns plus omega n square. Okay, this is your narrow bandpass function. That means a given system consisting of, okay, two responses. One is a narrow bandpass function, another one is what? Low pass function. So narrow bandpass function will have a frequency response something like this, and low pass function will have a frequency response something like this. Okay, and it's all, the cutoff frequency of this all depends on your damping used in this. So that means it depends on the parameters B, C and D. Okay, so B, in fact C and D decides the natural frequency, and the damping accordingly will get either a Butterworth or Chebyshev response, something like this. Okay, so but we did not get into that deeper. So it is simply a low pass structure. This is a narrow band pass structure. So if you're adding the two, means the result is going to have a frequency content ranging from 0 to till that, okay, upper cutoff frequency of your band pass system. So this is going to have a omega 1, this is going to have omega 2, and this is going to have a omega c. Okay, so but values are not given. It's all about how you configure your given system. So then can you configure? So which one is possible, which one is not possible? So by tuning the values of A, B, C and D, which is possible, which is not possible. Can you configure this as a low pass filter? Means, so if A is closer to 0, you can straight away say that it can be configured as a low pass. Yes, it is configured as a low pass if A is closer to 0. If B is closer to 0, you switch off the low pass, it can function as a band pass. It can only. Okay, this is can. We can configure this as a low pass. We can configure this as a band pass. Then can we configure this as a high pass? Means, so the maximum frequency it can pass is, assuming omega c is less than omega 2, omega 2 is greater than omega c, cutoff frequency of the low pass, or even if you assume otherwise, no problem. So the thing is that we can't pass cutoff omega equal to infinity. We can't pass high frequency content to the output. That means it's impossible to pass the high frequency content, means it can't act as a high pass filter. That means the given setup, it doesn't have the high pass function. It has a low pass, it has a narrow band pass. So you can configure individually as a low pass. You can configure individually as a narrow band pass. So both low pass possible, band pass possible, but this is not possible. This is cannot. So this can be your right choice according to the problem. So problem is talking about only cannot. Okay. The system cannot operate as what? Okay. So it cannot act as high pass filter seems to be the good choice. But we have another option. Okay. In the race, it is an integrator. But remember, this is a multiple choice question. So we have only one correct answer. So we have to reject, we have to somehow show that it can also be configured as an integrator. How to show that the given H of S can be configured as an integrator, we'll see. So what we have is H of S that is equal to AS divided by A square plus CS plus D plus it is B by A square plus CS plus D. Same identical denominator, only the numerators are different. So here we have B, here we have AS. Now let me assume B tend to be is closer to 0. That means we turn off the low pass function as we imagined earlier. Now let us have only the narrow band pass. We'll tune this parameters. So when B tend to 0, H of S is getting closer to this, that is AS by A square plus CS plus D. Now let me divide numerator and denominator by A square. So the numerator will become A by S. That's a desired because 1 by S is an integrator. Okay, I wish to configure this H of S as an integrator. Is it possible or not? That's my question. So it is A by S. Then denominator is going to become, when you divide numerator and denominator by S square, the numerator becomes A by S, denominator becomes 1 plus, we'll get C by S plus D by A square. So this can be closer to A by S when C is closer to 0, when D is also closer to 0. Under this condition, I can configure my narrow bandpass function as a pure integrator as well. It's closer to integrator, so not a pure integrator. Pure integrator means C must be 0, D must be 0. So closer to integrator, I can configure H of S. Can also be configured as a integrator, provided B closer to 0, C closer to 0, D closer to 0. That means these are all the possibilities. Therefore, this is also possible. Okay, that means integrator configuring the given H of S as a integrator is also possible. Therefore, it is not in your choice. Okay, so 3 cans, 1 cannot, only 1 cannot. Who is that? Means I pass cannot be configured by using given H of S. So that is the right answer. So that's a very interesting problem comparing to the problems okay we have done today. So this is little interesting, playing in frequency domain, just giving two systems. One is a narrow band pass and another one is low pass, added with the 4 constants for tuning, and you need to imagine that what is possible, what is not possible. Yes, a good problem in electrical gate 22 paper. Okay, so do subscribe, will update you with one more problem.